hopefully it's working. Okay, so for those of you guys that have gone to the cross-campus science experiment thingamabob, hope you had fun with the kids, but hope you're also checking out the videos. Dean and Gavin, hey, how's it going? Hope everything's cool. If not, come talk to me, because you guys don't get to ask questions traditionally in the classroom setting like everybody else. Our goal today, for those of you guys that just aren't at school, I hope everything's okay. Okay, everybody who's here, hi. We're finishing related rates. We're doing as many examples as possible. I was reminding you that, number one, I had to adjust the calendar because of Friday. But number two, where we're going is a test, and the test is going to be Thursday and Friday. Woo. You guys realize this chapter is the word problem chapter, right? Okay. So the last 2 years, I've tried to fit it in one day, and basically I've given up. So I could have a test with like 10 problems. Wait, you miss one and you get a 90, you miss two, you get an 80, you miss three. Oh, that's bad. Or I give you a normal length test and I give you 2 days. Does that make sense? Now, with the 2 days, that's not me giving you the whole test. You get to look at the whole test and then take it at your leisure. That's I give you half the test the first day, the second half the test the second day. Sound good? Okay. So that's what we're doing. That's Thursday and Friday. Thursday is day 1. Friday is day 2. The calendar shows this if you want to go look at it. But to get ready for that, today we're finishing related rates. Tomorrow we're going over related rates questions with you guys up at the boards, just helping each other, getting participation points. We talk about the test tomorrow, so you guys have the details. You start working in class on the review. The review is due graded on Wednesday because the key is online. It's probably even. Did it pop up for you guys already? I had it like scheduled ahead of time. Okay. I didn't know if the calendar messed it up. Maybe I caught it in time. The review will probably pop up tomorrow then. Wednesday in class we'll talk about review questions. We'll do AP Classroom. Bring your phones. Lainey, you can use the computer. We'll do some practice multiple choice. And then Thursday, day 1. Friday, day 2. Is that cool? But if you guys don't mind, let's go ahead. I'm going to pause the video just for a second to pray for class. I've been just kind of praying. You can come by, find me during 7th period or after school today. Even if I can just pray for you if something crazy happened this weekend, I'd love to. But otherwise, let's just get back into whatever sense of normalcy we can as far as tackling this thing called related rates. We were doing this whole thing in your calculator. I just think it's a cool simulation. You get to kind of see the ladder falling in some way, shape, or form. And falling at different rates, which is kind of cool, because usually you're like, okay, whatever, they're changing at different rates, but we don't really understand. Sometimes the units thing at least kind of clicks as far as like, okay, if we're talking about a balloon, the volume, like centimeters cubed, would have to be different than like the radius, centimeters. Like they're measured completely differently. You have this 3-dimensional thing and this 1-dimensional thing. Of course, they would have to change different to each other. But when you have something like a ladder, like it's kind of confusing. You're like, what? Does it really? I mean, you don't usually watch people fall down on ladders, although some of you, I can totally see you like YouTubing some channel that's all about people falling down on ladders. But anyway, but the calculator simulation did show you that this one started off slow and then like sped up as it got closer to the ground, whereas this one, what did it say about the rate being pulled away from the wall? dx dt was constant, yeah. So this one was being pulled out at a constant rate, and yet this just went ahead and slipped down real fast. And if you guys thought about just your own experience, that probably makes sense. Like at first, I mean, even if you were standing on a ladder, it would be like, right? And then like it totally goes out from under you in the sense that it starts off slow and then all of a sudden it goes quickly there towards the end. But maybe you just didn't really think about that as being an example of why this whole related rates that are related mathematically, and yet they are different and unique from each other. We can use one to solve for the other. We were doing this whole example. We were playing with the graphing calculator, etc. But at the end of the day, we were supposed to be finding dy dt, right? And we got left off in the sense that we didn't get to finish solving. So how would we finish this example, guys? They said t equals 3. So what am I supposed to do with t equals 3? Because don't I need an x and don't I need a y? How are these functions or these equations given to you? Why did I change from the word functions to the word equations?
Because they're parametric, right?
Yeah. And how are parametric functions? Hey, what was weird about, I know, our endeavor card is still up, endeavor number 2. Don't we even have an endeavor number 3? What was weird about, now here's what's funny. There was a forever quiz a little while back. And I asked them about a tangent line. Guess what some of them put down on their card? The parametric version. I'm like, you haven't even learned parametric versions of calculus. It was up on the wall, so they were like, tangent line, and had no clue what was going on. Silly 80s kids. Yeah. They definitely got marked down for that. I was like, that was cute. No. Anyway, coming back. But for you guys, you should know what this is. Why is this weird? It's weird for 2 reasons. Which one? The slope. The slope. It's not just f prime of c, it's y prime of c over x prime of c, because the derivative of parametric equations needs y prime over x prime. Good. What's the other thing that's weird? Isn't it at? Wait a minute. There's a typo on my comment. Isn't there? It's not a typo because it's not typewritten, but it's handwritten. There's a typo. It'd be technically a hando, wouldn't it? That's weird. Because a typo, typewritten, handwritten, hando, that's weird. Anyway, coming back. What's wrong about what I wrote? I said at what? X equals C. But what's the independent variable for parametric equations? T equals C. And so, does C go in this x minus c spot like normal? No. Where does it go? Inside x of c and y of c, inside the t spot in x and y, yeah? So, can we revisit the question I just asked you? How are we going to get x? And how are we going to get y? If we know that t is 3. Did you guys see what they gave you?
Oh.
Say it. You plug it in, plug it in. Don't we just need x of 3? And y of 3? I heard some kiddos mentioning, I forget what or when. I think it was an email that I got. They were like, man, when it got to the parametric stuff, I got confused. Okay, so check it. Just like we had to reevaluate, just like we had to kind of change how we did the tangent line, with parametric equations, we might have to kind of change how we do related rates too. If we need an x, maybe we have to go plug in a t. So x of 3, oh, no big deal. It's just going to be 6. And y of 3, no big deal. It's just going to be 8. Okay, right? 2 times 3 is 6. 6 squared is 36. 100 minus 36 is 64. Square root of 64 is 8. Mental mathers, give me a thumbs up if you like that. So now what do we have to do to solve? Oh. Now, could some of you make mistakes at this point? Mm-hmm. So if it's a long answer, what if we do this and be like, forget it, right? Oh, no. It's a word problem. Do we have any units? Feet per second, right? I know for sure, definitively, and maybe you did too, that it was feet per second. Why not feet squared or feet cubed or second squared? Yeah, I mean, the rate of x is feet per second, so wouldn't it make sense if this is changing in feet per second, so is that the same dimension, the same measurement, it's length, right? But also, what's y? Isn't it the height on the wall? Isn't that feet? And then what's t? So the units match no matter how you look at it. Okay, so with that, in theory, how fast is the top of the ladder moving as it hits the ground? Well, that's exactly what we just found, isn't it? That'd be negative 24 all over 16. We could reduce it, but That's okay. And why is it a negative rate again? Just real fast. Falling, aka what's y specifically, the height on the wall, what's it doing? Decreasing. Perfect. And why was this a positive for the x? Good. Nice terminology. All right, cool kids. So with that, let's not stress. Let's not stress. Let's pause here. If you guys want to see what I'm skipping, sorry, the wrong line. All I'm skipping is then basically saying, hey, when you have a function that's a bit more complicated with multiple variables like v and r and h, and you go to take a derivative of that, you're going to have dv dt's, dr dt's, dh dt's. You're going to have to do product rules, right? We're going to have a lot of rates that are related. So it's something that I would say more kind of as a trick or as a hint, if possible. Relate R with H. You could just start with this equation and just take a derivative with product rule and be like, okay, it's nasty, let's go looking for stuff. But you could have also gone looking originally and been like, hey, is there any relationship between these two where I can have this little snazzy, I don't know, something like r equals 1/2 h, you could actually plug in and get rid of r and have everything in terms of h, which would make your derivative a lot easier. Does that make sense strategy-wise? There are lots of variables. Sure, we could just go deriving it, but we could also maybe try to get rid of some of those variables. But here's something else. I thought it was super interesting in how your book put it, and our book does have some really interesting insights into calculus. So just reading it real fast. What has always distinguished calculus? What has always distinguished calculus from algebra is its ability to deal with variables that change over time. Example 1 illustrates how easy it is to move from a formula relating static variables like v and r and h to a formula that relates their rates of change. Simply differentiate the formula implicitly. I know simply is a product rule, I know, but still, simply differentiate the formula implicitly with respect to t. And then all of a sudden, this introduces an important category of problems called related rates. That constitutes one of the most important applications of calculus. They're saying, 1 second, you have an old school geometry formula, v equals 4/3 pi r squared h, and you're like, cool, I can plug in an r and an h and get a v. Plug in a v and an r and get an h. Plug in an h and a v and get an r. That's all you can do with that formula. But if you take one derivative, just knowing how to derive implicitly, all of a sudden you can have it moving and changing and relating in a way that you can deal with, or you can show and explain rates of change. Anyway, just re-emphasizing, calculus is the math of change. Okay. Here's the deal. Does the book have a strategy for solving related rate problems? Yes, steps 1 and 2 and 3 and 4 and 5 and 6. Dang. If I were you, I'd grab out your phone and take a picture of it. I wouldn't write it down. Could I have made some sort of forever card that you memorized for related rates of change?
Yep.
Yeah. I could. But with all of this nastiness, which is good, it's good to think about, especially if you're stuck being like, okay, step 1, have I? Step 2, have I? Step 3, have I? It's not bad. It's not awful. Did you get it? Okay. I tend to simplify it a little bit differently. They have 1, 2, 3, 4, 5 sets. It's great. It's good. I might refer back to some of it. I just say 1, 2, 3, 4. But my 1, guys, is it really that different than any word problem that you ever see in calculus? The given and the find. Oh, yeah, that's what you always did. Oh. Hey, isn't that what I have you do every time you write down the directions and the problem details? What are you supposed to do and what do you have, right? What are you given? What are you supposed to find? Now, drawing a picture, labeling the variables, yeah, that's cool. And technically, I know, can you see the red? I'm sorry. Fill in the constant values. Remember the ladder was 10. Was the length of the ladder changing at all as it fell? Not in our scenario. Yes, the ladder can break. Maybe it's one of those expandable ladders and it's shrinking at the same time, but not in our example. Our example was 10. It was always 10. Make it 10. Its derivative will be 0. Life gets easier. Think about the motion. Label the constant values. Number 2, figure out the relationship. Is it just Pythagorean theorem? Write it down. Is it the volume of a cone? Write it down. Is it ratios of similar shapes are proportional? Ooh, that's when they love to throw in. Write it down. Figure out any relationships between your variables. Maybe it's a big geometry formula. Maybe it's a little detail that they put in. Once again, you can plug in any constant values. If anything is staying the same the entire time, but only if it stays the same the entire time. Number 3 says use chain rule and implicit differentiation. 2, my shortcut way is take ddt of both sides, right? I'm going to write a quick little note. Substitute. That means plug in, right? Out. Substitute out. I changed my mind. Substitute out any bars, any variables, if possible. Substitute out any bars, any variables, if possible. Just a second ago, v equaled, or it still does, but v equals 4/3 pi r squared h. I said, man, if you get rid of that r, it'd be great. It'd be easier. Man, if you get rid of that h, that'd be great. It'd be easier. If you do have multiple relationships, maybe a big geometry, but maybe a little detail, maybe you can use that to substitute out some of those extra variables. It'll just make the derivative easier. Careful, only plug in constants that are true the whole time. We can substitute out any variables with relationships if it's there. Then take the derivative, then plug and chug. But remember, when you go to substitute all the knowns, sometimes you have to search for missing quantities. Wasn't that ladder example a good one? T equaled 3. Well, great. I need x and y. You have to go look for them. But no big deal. They were there. They were able to be found. Now, that's my summary. As you guys are writing that down, my quick steps. Over here, their number 1 was understand the problem. Great. Good. Thanks. Understand the problem. In particular, identify the variable whose rate of change you seek and the variable or variables whose rates you know. I do like that terminology. Figure out what you're seeking for and figure out what you know. But in my mind, it's like, okay, the given's in the mind. Number 2, develop a mathematical model of the problem. That super snazzy terminology you saw it in pre-cal, mathematical models with direct variation, inverse variation. So they're saying develop a mathematical model. That's when you're making an equation relating to variables, but you're not making it up out of thin air. You're using your mathematical training in geometry and in different, like trigonometry, in order to get those. And they say draw a picture, especially of geometric figures, label all the parts that are important, distinguish constants from variables, what's changing, what's staying the same. Only constant quantities can be assigned numerical values at the start. Okay, I said that. Plug in the constants if they stay the same the whole time. And it's constants. Number 3, write an equation relating the variable whose rate of change you seek with the variable whose rate of change you know. They say, sweet, if you have these, and you need h's, try to get rid of the r's. That's kind of what I said by substitute out any guys that you don't want, or any guys at all, if possible, to make it simpler. Then they say differentiate both sides of the equation, substitute values in that depend on time, and then interpret the solution with some sort of word, sentence, justification, analysis, probably using the word increasing or decreasing. So guys, now I just have examples. Some of them are going to be easy, some of them are going to be rough. But this first one, he's not bad. Why is he not bad? If you look at him, just real quick, why is he a nice and easy?
Less words.
Less words, there are fewer words. They give you an equation, and then they give you a nice little mathematical notation exactly what they want. Isn't that cool? They give you nice, clear, what they want.
Sorry for the interruption. I did not know. And I looked on the test calendar. No, I know because I am in the PSATs Wednesday. And I couldn't do this first period Thursday. So I wanted to know because the test, the answer I got is 2. So maybe the kids had said, we have to so I went in. This is
So, breaking news! Did you guys know there's a minimum day on Friday? Yeah. Thanks for saying it out loud. It wasn't on our calendar, and Mrs. Hammond hasn't sent out. The nice 10 minutes ago. So I can still spread out the test. It just won't be as much time as I thought, but I will take that under consideration and try to make it reasonable. Sound good? I mean, we're already spreading it out. I just have to think about it. She wanted to make sure she saw on the test calendar that you guys had a day 2 of the test. Okay. Anyway, Mrs. Johnson looking out.
Why is there a minimum?
There's a prospective campus preview on Saturday, and so they're trying to give teachers half of the day to prepare for it. We would rather have school, but you guys are just fine with the minimum. We're not going to win that battle. Guys, why am I just going to write down really quick dy/dt is equal to 2x dx dt? And why am I going to show with that? And why am I going to show with that?
Plug it in.
How easy is that? Okay, so if you go from that to a hot air balloon. Oh, you can draw it. A hot air balloon is rising straight up from a level field, tracked by a rangefinder 500. Okay, hold on. Rising. I always put arrows on things that are changing so that I don't accidentally label something a number that is changing, that is moving. Does that make sense? But why am I going to do this as a 500, even though I'm just going to put this as a 1? The rangefinder is not moving. What's moving? Yeah, the balloon is. And it's tracking the balloon. Isn't this similar to the camera problem last year with the rocket that was lifting off and the camera was like, oh, hi, as the rocket was moving, but the camera was not getting closer? The rangefinder is fixed. He's just tracking the hot air balloon. At the moment, the rangefinder's elevation angle is, oh, crud, angles are important now? Wait, can I label that with a number? Anytime you see this, you should beware of putting a number. Why? It's a snapshot in time. But what was the angle a second ago? Lower. What's the angle going to be soon? Higher. I can't label that pi over 4. What do I have to label it? Got it. Does that make sense? Changing. Same. Number, variable. Sorry. Variable, number. Okay, so what am I supposed to do? There's not a clue, but yeah, how fast? That's what I'm supposed to be finding. How fast is the balloon rising? Which rate do I want? I have 2 variables. Which one do I want? Good. I want to find dy dt such that at the moment beta is pi over 4 and the angle is increasing. Aha! d theta dt equals 0.14. Does that make sense? Yeah. Now wait, we would have to have some sort of equation, right? We have to make a mathematical model. What models the y changing, the theta changing? Forget about the changing. That's a derivative. Forget that. What models a triangle with an opposite, an adjacent, and an angle? Got it, coach. We okay? What would make your life easier when taking a derivative? Oh, look. No more division. Some of you don't do so well with the 1 over 500y. It's really just a constant. Now what would you have to do? Can I just do a little? No, I want to just look at other things, so I'm going to stop on this one for right now, because you guys can see plugging in wouldn't be too bad. Watch out for radians. We're going to have to go over radians when we go over homework questions anyway. So this whole, wait, this is changing in radians per second or per minute. And this is changing in feet. How do I do what you can? The units are going to be a little funny. But is the math that hard as far as setting up? Do you guys see how I read that problem now? And how I started to put a number and I was like, no, it doesn't make sense. What was I thinking? Maybe I should have put an arrow there. Does that help? That's changing. That's changing. What's staying the same? What else do we get? Oh, take a picture. Guess what this is for? Unit analysis, radians and feet. Take a picture. If you get to it in homework in a place where you have radians and feet, just peek and see. Does that make sense? We'll go over it tomorrow when everyone's here. This is just a little unique. Dimensionless. Ooh, that's interesting. Okay. A pebble is dropped in a calm. It's like classical music in the background. Maybe Thoreau is riding over to the side. Causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a rate of 1 foot per second. Okay, is anybody else lost yet? What kind of picture? Yeah. It looks like a pebble is dropped, right? And then what? Ripples. You see it? Oh, okay, the circle is expanding. Hey, it's like that one. Okay. Although that one's like trigonometric ripples, so let's not go trigonometric right now. Yeah. So the other thing is to do simple circles. Okay. So if circles, it's expanding, it's going up. The radius of the outer ripple is increasing at a rate of 1 foot per second. The radius of the outer ripple. When the radius is 4 feet, at what rate is the total area? Oh, okay. This wasn't super confusing. I know it says radius of the outer ripple, but maybe that just means from where it was dropped to where it's at, which is always increasing. Does that make sense? So just like we drew a picture a second ago with a hot air balloon in or paused at one moment of time, we had an arrow saying, no, we get it. He's rising. He was here a second ago. He's here later. We're just doing a representative little line. Same here. We could make it ripple here or here or here. But check it, guys. Radius, there's one. What was the other important measure? See it? There's other important stuff. But radius and area, do I need to care about like an inner and an outer and in between? No. It's just radius and area. Oh, what's my relationship? As easy as that. Now it could have been so complicated. Wait, I have outer ripples and inner ripples, and you're just thinking about ripples for like 10 minutes, and all of a sudden all your time is gone. Just keep reading and be like, oh, area, radius. Okay, so what are all my givens? What am I trying to say?
1 foot per second.
Okay, I'm trying to find the ADT. Good. Yeah, because coming back, when the radius is 4. Oh, good, because that's something that's true the whole time, not just at an instant. So, and why are you making DRDT positive? Got it. So, I mean, could I draw a picture and be like, hey, for that ripple, I have an area. Yay! I mean, I guess I could. This doesn't really need a picture. It's just A equals pi r squared. So wouldn't you guys just take DDT of both sides? And not just be the ADT? Now, what's been easy so far? The derivatives and the plugging in. Are the words getting a little bit nastier as we go? A little bit. Maybe we can get to some where the derivatives and the plugging. No, it's not just that. Yes. You ready? Oh. Right. Okay, the words might get nasty, but what's nice about this right away is you guys look at it. It gives you a formula. Oh, but what's nasty about the formula?
3 variables.
3 variables means a product rule unless we can get rid of mass or unless we can get rid of velocity, right? Oh, stink. Okay, so hold on. What do we see? Decreases. This is what kind of clue? Yeah, and it's a dm/dt, right? Is that good? Okay, so hold on. I got that. When the, but careful, that's a when, right? So that's like a such that?
Yeah.
That's not something I can like plug into a picture. I'm not taking a picture anyway. This is the velocity is, oh, I know that too.
Yeah.
And increasing, who's increasing?
Velocity.
Good. I have kilograms and meters and seconds and okay. What am I supposed to be finding? Ah! There's something called joules? Google it. It has to do with kilograms and meters. Seconds, it's a thing. Hey, give me back. Not that kind. He has a smirk as he's so he's laughing at you laughing at George. Okay, give me back.
Thanks.
What's the one thing? Like, guys, was it really that bad picking out clues? No, but what are you gonna have to remember? Is there anything to get rid of M or to get rid of V? Is there any like, hey, M is 5V, go plug in? No. Look, they gave me a dV/dt, they gave me a dm/dt, and they're asking me, what do I have to do? Sorry. You have to do product rule. To get your dk/dt's, dm/dt's, dv/dt's, you have to do second V first plus first V second. Second V first, there's your dm/dt, right? 1/2 dm/dt. First D second, there's your 2V dv/dt. You gotta do it legally, but you're gonna be able to plug in just fine. So what was harder on that one was derivative. How about this one? How many variables?
3.
Ugh, there's not even a picture. Oh, but there is an equation. Oh, come on, but this is very specific physics, right? Like it's in context of living physics. Okay, so what do we have? We have an equation. When t equals 6. When? I see when. You guys see that? What's decreasing? Yeah. Due to the burning of his fuel. Good knowledge. What are we supposed to do?
How fast is
So I see a dm dt. I see a df dt. What don't I see? So even though this is what I want to find, go looking at your clues and say, okay, I don't have a dA dt, and if I go doing a product rule, I'm going to get a dA dt, but what do I have? An A. That I could take the derivative of. So couldn't I say dA dt is equal to 10t plus 6? How did I get that? I don't know. Oh, and I can plug in 6 and I have my and I can do my little. So just because you have 3 variables, does that always mean you need to get rid of one? No, sometimes you're going to have clues about all of the rates, so you have to do product rule. But could you also have some of those nasty ones where geometry comes to bite you in the butt? Oh, this isn't bad. That's like a, you can give you the formula, only 2 variables.
It's like,
You didn't have to take this actually.
I saw the font.
Pause. What do you see?
Bubble.
instant, when the height is 3 inches, the radius of the surface is decreasing at a, what is it? It's related rates. And guys, as you have something like this, and I'm not saying you need it in this problem, I actually don't remember, but as you have something like this where the water is funneling out, what's true about all of these rectangles? Sorry, triangles. They're getting smaller, but they're symmetric. They're proportional to each other. Which means the ratio of R over H is going to equal every other R over H. So if it's, for instance, 5 and 10, 1 second, guess what it's going to be the next second? A ratio that still equals 1/2. Does that make sense? Yeah. I'm just showing you the idea. We don't have to solve the effort. I've done as many practice things, tricks that I can. Sound good? Yeah. The best you can, relate rates, tomorrow with as many questions as possible, but you need to read, analyze. What do you get? What do you need to find?
I think we all were confused by the washes.
Oh, that's not what we're doing today.
You're saying the related rate.